Okay, this is Durwell King with Sampson Community College, and this is the MNT 110 class. And we're going to do just part of the class recorded. The first part of it we didn't record because it's a repeat on something that we did the other day. So this segment here is going to be on doing insulation tests on motors, how to wire them, how to wire three-phase motors on low voltage and high voltage, and how to do an insulation test to see is the motor bad or not. Is it shorted to ground, or does it have a broken winding on the inside? So we'll start out and let's look at two general types of motor windings that are most common in the industry. And most motors I've been around over the years, from where I've been, and that's only speaking from where I've worked, okay, which is, in a couple plants. Most of the motors were considered to be internally. This is three-phase motor over here. Most of them were considered to have a configuration of windings called Y. It's a WYE is the proper way to say that. It's a Y-wound motor, and it's shaped like the letter Y on the inside. These are the internal windings in that motor, and that's how they look inside. That's the way it's actually made. It's in a Y configuration. And you have 9 wires, T1 through 9, that are loose whenever you go to the cat head or the enclosure. As you see there, you have those 9 wires there. Some of them are already been paired up. But there's a total of 9 wires, and whenever you wire a motor, you got to decide what to do with them. That's going to be based on, are you wiring that motor for low voltage, which will be in the range of 208 to 240. If you're going to go low voltage, you do this configuration with your wire nuts. If you're going to go high voltage, 480, or maybe as low as from 460 to 480, you would do this connection with the wire nuts, and that same motor would run on low voltage or high, and it would run the same horsepower. No difference in horsepower. And so let's talk about the how do you do it if this motor is going to run on, say, 240 volt three-phase. So here's how you do it with the wire nuts. You come from the motor starter. Let me grab a starter real quick. So you have the motor starter right here. The 3 phases come into the starter here, on L1 through 3, and then they leave on T1 through 3. So they leave here, and picture it right here. But you got the starter. You're going to go from T1 to wire number 1 and 7 at the same time. So you're going to have a wire coming from here. You're going to take a wire nut and join this wire with 2 more wires that are in the motor. So 1 and 7 are labeled in the motor cat head. That's going to give you a total of 3 wires in that wire nut. The T2 leg from the starter, it's going to come in and join with 2 and 8 in the motor. That gives you 3 wires in the wire nut, right? Then you come from T3 on the starter, and it joins with 3 and 9 in the cat head. That gives you 3 more wires. Then you take 4, 5, and 6, and you bundle them together, and you don't connect them to the power line. They just are isolated bundle together, 4, 5, and 6. That's 3 wires together. So if it's a common Y-wound motor and you're on low voltage, each wire nut has 3 wires per wire nut. Okay? And then what you've done here is when you hook it up that way, you have put these wires, you have produced not only a Y winding, but you have produced a double Y, because look, the 4, 5, and 6 in here, if you look, 4, 5, and 6, whenever you join those together, it forms another Y like this on the outer part. So it's a double Y, and the Y's are in parallel. They're in parallel because of this. Your first leg of the 240, the T1, it goes to this outer leg of this one, and it goes to 7 here and here. The same hot leg goes to 1 and to 7. The next hot leg goes to 2, 2 and 8, 2 and 8, and then the third leg goes to 3 and 9, and to 3 and 9. Now, so you've actually fed in your 240s, each one of them legs, to here, here, same one here, and then the same one here, here. Then you're joining 1, 4, 5, and 6 together here, which produces another Y like that. See that? And they both Ys have the same voltage on them, therefore they're in parallel. So when you go low voltage on a Y motor, it's called a double Y. It's a double Y. You have 2 Ys in there, and they're in parallel. Okay? And that's the way most motors I've worked on are Y wound. It doesn't tell you why on the nameplate. It doesn't tell you that because most motors are Y wound. The only time you see what it tells you what kind of a winding it is when you come up with something that's called a delta. So let's flip over to delta. Delta looks like a triangle. And when you see a delta wound motor, then it actually tells you the word delta. It'll say delta wound right on the nameplate. I've got one we're going to show you back in the cabinet. We're going to do that really quick here just a second. Show you every delta motor I've ever seen in my life, which is not a lot of them. They always tell you that it's delta right on the nameplate. It says delta wound. It tells you right on there. Okay, and the difference is between the delta and the Y is this. In the Y, embedded in the center of it, you have a permanent connection of 3 windings that you can't interrupt, that it's actually a fixed connection in the heart of the motor that actually makes it to be a Y wound motor. There's a Y built into it in the heart of that motor. You can't change it. You can't make it something else. On the delta, there's no Y connection in there built in, but here's what you do have. You've got these 2 windings are connected internally. So the T1 lead that comes out of the motor, it's already hooked up the 2 ends of these coils. And then these ends are free for you to do whatever you're going to do with it over here. These 2 ends are tied together already to T3 lead coming out of the motor. These are already hooked together permanently. So you've got some connections there that are already permanently done in the motor. You can't change them. And overall, the configuration looks like a triangle inside that motor, and it's called delta. That's a Greek symbol. Delta is a Greek symbol. That's what they call it. And so here, let's back up to the Y configuration. So when we did this, we said we were producing double Y in parallel for 240. So what happens if we hook that motor up to high voltage? The same motor will go high voltage. Now, by the way, whenever I'll just save that for later. Let's say we're on 480 volts coming to the machine, and the same motor can run on either one of them. So then you have the incoming power from the starter. T1 from the starter, it runs to just 1 only. So wire number 1 in the motor, you run from T1 just to 1 only, and you wire another. The T2 goes to 2 only. T3 goes to 3 only. And then you put a wire nut around 4 and 7. You put another wire nut around 5 and 8. You put another wire nut around 6 and 9. Now this lines up with your dial pad on your phone. So I'll show you a little shortcut. If you're dealing with high voltage and it's a wild wound, here's how you can remember how to hook them up. Your dial pad actually tells you. So go to your phone and look, the incoming wires goes to 1, 2, and 3 from the starter. And then you put a wire nut around 4 and 7, another wire nut on 5 and 8, another wire nut on 6 and 9, and this matches the dial pad. Okay, so that's a shortcut way to remember if it's high voltage 480 and it's a wire wound motor. Okay? So what do you have here when you do it this way? A while ago you had parallel winding in low voltage. Now you've got something called series, because look, The incoming line comes in here, here, and here on the outside, right? You've got T1, T2, T3 on the outside. You put a wire nut around 4 and 7, a wire nut here. You put a wire nut on 5 and 8. You put a wire nut on 6 and 9. And now this is considered to be series. These are all in series, not parallel. So if you measure with a voltmeter between T2 and T1 and T2, you'll measure 480 volt there. If you measure between 2 and 3, you'll measure 480 volt. If you measure between 1 and 3, you'll measure 480 volt. And the windings are in series, not parallel. And you say, well, maybe would the motor maybe run twice as fast or have twice the torque? It would not. I'm going to show you why that is. Let's do a breakdown of this. Now, if you have 480 volt across here, 480 volt, and you have 4 windings in series in that set there. And I measure 480 across there. And we know in a series circuit, if you got 4 coils in there and they're the same resistance, each coil, that voltage is going to divide up in 4. You'll drop a quarter of it here, a quarter there, a quarter there, and a quarter there, right? So what's a quarter of 480? 480 divided by 4. 120. 120. So you will measure 120 across this one, 120. You'll measure 120 across that one and 120 across that one. Seriously, if you put your probes in there, that's what you get in the motor. You get about 120 across each one individually in series. Or if you measure here to here, you would measure the 240. So each winding is getting about 120 a piece in this case, and the same thing here. If you measure across here, same thing. But what happens when you go parallel? Let's just back that up. Let's erase this. Let's go parallel now. Get low voltage and find out, do the windings get the same voltage? So we go back to here, and now we have the 240 is hooked up to 1 and 7, right? So you have we're going to say we got T1 here, and we've got T1 here, right? And you got T2 at 2 and 8. T2 here, and T2 is also right here, right? And then you've got T3 on 3 and 9. T3 here, you've also got T3 showing up here. So we know if we measure from 1 to 2, or 1 to 3, or 2 to 3, it's going to read 240, right? So right now, the inner Y, if I measure from here to here, what will I measure? T1 to T2 on the inner one now, over here. What would I read? 240. I would read 240 across these. Here I've got 2 windings in series. If I've got 240 across there, how much voltage drop is across each one? 120, exactly, 120 again. Now, if I measure from here to here, what 240, which means that then I have 2 windings in series, and how much I take on it? 120. I get 120 across those. Now, when you go and do 4, 5, and 6 together, you put 4, 5, and 6 together, you're producing another Y with these 3. You're basically moving them out to the side, and you're doing this. You're producing another Y here with 1, 2, and 3 on the outside. 1, 2, and 3, and the center is 4, 5, 6. 4, 5, 6. You see that? So you produced out of these 3. You moved them out and done this, and you've actually got in this one you have T1, T2, and T3, right? So if I measure here to here, what do I have? I've got 240. Let's draw the windings here. You have here, there, going, winding here, out, winding there. And so you have 1, 2, T1, T2, and T3, right? These 3 are out here now. So if you said I'm going to get 240 across this outer wire, right? That's out here, 240. So if that's so, then I have 2 in series. How much are they getting a piece? They're getting 120, 120. And I measure from here to here. What do I get? 240. And in series, I get 2 here, and they have much a piece? they still get 120. And so the difference is in both cases, whether you're doing low voltage or high voltage, each winding still gets the same amount of voltage, so it puts out the same amount of torque and the same horsepower and all that stuff. You get the same horsepower no matter how you do it, because you have reconfigured going from a double Y parallel to a single Y series in high voltage. And you end up, it's all in a matter of going series parallel internal to the motor. And that's why it works the way it does. Okay? The next thing is, how do you test this motor to know if it's bad or not? So does that make good sense for what we just went over? Okay, good. So what happens with motors whenever they go bad is typical. Got a motor right there. Now you can have the blue box. Yes, sir.
Key message.
Yeah. Now look, so what are the possibilities? What could go wrong with the motor? Well, you can have the bearings could go bad, it can lock up, right? You can actually feel that if it's obviously locked up. So that's a physical thing that can happen there, right? Then you can have the issue going on with the windings in there, where you can have a winding that could do two things. The motor windings in there, you can have a winding that can actually short the ground. Let's just draw the ground thing in there. You can have a winding that can short to the ground symbol, to the ground, which would be the frame of the motor. So the frame of the motor would be grounded, okay? Like we have here, we got a ground wire here. These windings are supposed to be isolated from ground because of the insulation around it. So what happens is when the insulation gets hot and it cracks, or you have, if they age and they dry rot, they can dry rot, or they can get hot, crack, or melt for various reasons. Like if the bearings lock up and the motor gets in a bind, and maybe the motor starter, maybe somebody didn't set the overload correctly on the motor starter. There's an overload on here. There's a dial, and that dial can be adjusted for so many amps. Maybe somebody has cranked it up way too high, which happens. They crank it up way too high above the proper rating, and then the bearings lock up, and then it overheats the windings because the starter didn't trip out in time. And so you melt the wires, you have a meltdown. Okay, so that is just a domino effect that can happen. So let's find out the two possibilities what happens to the windings when they go bad. So here's what can happen. One of two things. You can have a winding in there that can actually have a short circuit to ground, because it cracks or melted and it lays over on the frame of the motor internally, and it has continuity to ground. So it's a short circuit to ground. That's typical. Now you can have something else that I've seen happen, that's very rare, but you can actually have a winding that can break open, that can burn open but not go to ground. That's called an open winding. So if you get one that actually burns in too internally, but it stays free and it doesn't hit the frame, then when you do a test to ground, this motor's going to rebound. It won't rebound the ground. But if it's got a broken winding in there, then it's going to be an open circuit, and there's a different way you have to test for that. So when you check, first of all, to see is it short of the ground, you're going to read with a meter from each one of these outer legs to ground with a special meter. And you're going to find out that you have continuity to ground. If you don't, then the next test is going to be checking continuity through the winding, like this. We take our meter. Yeah, where's the meter at? Your next test would be checking continuity through the winding. So you would simply put the meter on, like that. And you're just going to go up here, and you're not going to check the ground, but you're going to check through the motor. And you're going to go from T1 to T2. When you do that, you're going to check continuity through this 4 set of windings, through it. And that's going to tell you if you have a broken winding. If it says, oh, well, you've got a broken winding, okay? And then you're going to check from 2 to 3. And that's going to get continuity internally through those 3 windings. That's going to tell you if you've got a broken winding in there somewhere, or a wire nut that's come off in the cabinet. So your wire nuts, if one of them pops off, it's going to show you there that you have an OL, this over limit there, and you need to check the wire nuts first. And if they're good, then you've got a broken winding in there if it says OL. And then you can check from 1 to 3. You can check this way. You check the 3 directions here, here, and then here. And if you get OL on any of them, you've got a burned up winding in that motor. So that's your second test there, is checking leg to leg through it on with no power on it. Okay. So let's check a good one, then we're going to check a bad one. Okay. Now doing the first test, we're not going to use a regular ohm meter, because look, sometimes you can have a short circuit to ground. And if you read from T1 to ground, in some cases, when you read from a leg to ground, sometimes it will be a high resistance just above the capability of just picking it up. What do I mean by that? This meter won't read no higher than 1,000 ohms. It says 1K. See that? That you can have a high resistance ground in here that can cause problems. It can be higher than 1,000. It can be up around 2,000 or 3,000. It can be 500,000 ohms and still be a problem. Okay. Seriously. So this meter is not guaranteed to find it if you check from a leg to ground. It will, in a lot of cases, it will find it. Check 1, 2, 3 to ground. In a lot of cases, it will see it, but it won't catch it every time. And when it won't catch it, then you use this meter.
Oh, okay. Then go to the top of it. He's got a point in the side. Oh, my goodness. 8 hours just back here. I will the first time yesterday about 2 minutes. Really? Not 2 minutes. The welder at work from 110 or 240. And that's 110, but that's all I can get this.
Okay, so here, this is something called an insulation meter, insulation test meter, or mega ohm meter. We're going to go around this side to do this, to see that. So we're going to move the camera. Y'all kind of hang on whoever's watching. Okay, come on this side now. We're going to view from this side. You come on this side. So the best way to test the motor is like this. Let's get our test sheet out. Y'all get your pen ready. Something to write with. I don't have two. I got one. Just share it, yeah. Now, if you look closely here, this meter is called an insulation multimeter. It's a Fleet 1587. It does insulation testing plus a lot of other things. It's a great meter. And so the way this thing works is like this. Got a special plug here that has a push button on there, and the push button is these two terminals here. When you hit it, it tells the unit to put the high voltage on this line, which comes in through that. So it's a special plug. Goes in the orange connection there for insulation testing. And then you got to put a common, not over here, but over here for minus on insulation in the orange. You see the orange right in there. So we take our regular plug that would normally go on the right side, and we move it over to here. So it's going to work in the orange area for doing insulation testing. Yeah. And we're gonna pull these off here, and we're gonna use the clips. So that's convenient there. Test lead set. And that's the banana plug connection. We can put a clip on there. It's a spring loaded light connection there, so we can do that and it grabs nice like that. So the first thing you'll do is I'm going to show you what this thing will do based on. I'm going to let this meter over here tell you what this is doing. So we're going to come over here to insulation in the orange, and it will go from 50 to 1,000 volts. It'll produce that, and it says low battery. We're going to go ahead and try it anyway. But I've got batteries. Let's just try the first time and see if it'll be fine there. It's not going to work. We've got to put batteries in. Yeah, we got to put batteries. We've got to put batteries in real quick, and that's fine. There's right on the back of the part there, those AA. And actually, sometimes it's got to be. Yeah. That's not a big deal. You take the skin of this thing off like this. You got to peel that off, that protection there. And it takes four AA batteries. Let's get this here up and out of the way like that. You flip it over, and you can actually turn that with a coin or with a little screwdriver, something like that. You go to the like that. And that goes to your batteries. It has 4 AA's and it has a fuse. Sometimes if you hit something you're not supposed to, it can blow a fuse, and so it does have something to replace the fuse. So we go in here like this, and we pay attention to the polarity. They alternate one of them alternates from different position. And hopefully, and I had to put that in there, that shim, because the batteries are loose in this thing, and the foam rubber kind of got compressed. So if you don't do that, the batteries will move around in there. It's actually still saying battery. That's the fuse there. Give me a couple of different batteries. Let's just try a couple of different ones. Sometimes when the shelf life on them can be the issue. Sometimes. Okay. Try those. Okay, let me grab a different, meter. I've got other meters like this. Give me a second to grab a different meter. I've got access to another meter, okay? Y'all hang on. I'll be right with you. I've got another meter I can get a hold of real quick if you just bear with me. Bear with me. Go ahead and make sure this is wired for high voltage, okay? Wired for high voltage. and then check through the windings like it says on step 2. Get a resistance reading from 1 to 2, 1 to 3, and 2 to 3, reading through it in ohms, regular ohms is the best. Okay? Make sure it's on high voltage. And kind of be careful there about the camera, kind of let it stay what's not going to
Oh, there's 3. There's 1, 2, 3. What's it say?
Maybe that's what we do 1.5. Maybe go 1 to 2, but even if it's 1.5, it might be dead. Because it's probably 1.5 volts. Well, it's got 2028 on it, but that don't mean they haven't used it and put them back in the daggone thing. Yeah, because if it's less than 1.5, then 1.4, 1.3 is all right. Low.
What do you say to check on this thing?
Resistance.
Resistance what?
I think it's
T1 to ground. That's what we're going to do.
all these batteries got less than 1 volt.
Okay, so that means the batteries are weekend. Okay, I got one to work. Let's switch over the lead.
Yeah, that'll make it.
It's not there. You're not going to read to. No, you don't do it that way. As far as did y'all do the readings through the motor?
We're trying to make it better.
Okay, let's back up. Let's do the insulation test first. Okay, let's plug this into here. and then the common lead goes into here. Where is that? Let's get the clip. Even though it's showing a battery symbol, it will actually do it, and we're not going to put batteries in there. No. So look, for the range, we're going to select the 500 volt range. It'll actually put 500 on the motor, 500 volts. It'll put it on the motor and then test it. So we get right around here. Stand right here. So this thing's going to produce 500 volts. When you do that, you put the range is adjustable. If you wired that motor for 480, you go to 500 on this. If you wired it for 240, then you're going to set that setting down lower, around 250. Okay, we're going to go to 500, and you got this here set for high voltage. Yes, you do. And so we got the 1, 2, and 3 there free. I want you to watch. I want you to watch what happens. You get the other meter out. We're going to show you how. Let's just take these. And let's have this meter here and put it in clip red to red and black to black. And don't touch it. Don't touch them. Put your hands way out here. Right. So what we're going to do here is we're going to demonstrate that this meter here is going to tell you what that one's putting out, because we put them basically tip to tip. So when I can hit the test button here, or you can hit the button here. So I'm going to let you hit the button there, and it's going to put the 500 volt DC over here. 520 volt, 523 DC, it shows up over here. So it actually did do that. Now let go. So you see that it does do that. You don't want to touch it with your fingers. It can light your world up. Okay. So now, unhook these. And so we're going to go to this motor here. This is a good motor. You're going to check from each lead to ground and hit the button. And here's what your limit would be, your recommended number. By the lab sheet, it says a good motor reads greater than 1 megohm from each leg to ground. So if you're above 1 megohm, you're fine. Less than 1 megohm, you're bad. Okay, so hook it up, each leg to ground. And you make sure that the other leads don't hit anything, or it's just going to throw the reads off. Okay, so you're doing that, he's going to hit the button, and we're going to get a reading here. And what does it say? It says greater than 550 megohm. So that's the highest reading it can read. Now watch, you take it loose and have it in the air like that with touching nothing. Hold the button with an open circuit and watch it. Greater than 550 megohm. That's like an open circuit because it can't read no higher than that. It can't read no higher than 550 megohm. So that leg is okay. Go to the second leg. And hit the button. Greater than 550 million ohms. So if it's greater than 1 megohm, it's good. Okay, go to the third leg. Get it again. Greater than 550. See the greater than sign? It's way above the meg, so it's fine. That's the voltage it's producing that it's sending out to the motor. It's sending out 526 volts. DC is shooting out to it. Okay? So each leg to ground is fine. Okay? And then the one over here is actually bad. So we're going to do a continuity test through this one. But before we do it, while we're doing leg to ground, we're going to shift over to this other motor that we know is bad. So Butterball sent that one. But you're going from, you can find the 1, 2, and 3. So look at here. He's gone from leg number 1 there, and that leg number 1 is fine. Leg 2, 0.2 megohms. So that leg right there is bad. That's a shorted out motor lead there that was sent over here just for the purpose of showing you this stuff. And then you go from 3 to ground, and it reaches 0. So that's actually horrible. That's like, you got 2 legs that are short of the ground in that motor. That motor's definitely bad. Now, in some cases, a standard ohm meter checking with ohms, going from each lead to ground, a lot of times that would catch it, but not always. Not always. I've seen cases that it would not catch it, okay? So that's your first test there. And so over here on your lab sheet, you're going to put on here, put greater than 550 megohms on all 3 of these. The next one, we're going to check continuity through the motor from T1 to T2, 1 to 3, and then 2 to 3, going through the motor on regular ohms. So here, you go to regular ohms, you've got to move this lead here back. Or you can use this meter here. If you're using this one, look, you got to move the wire back to here and get out your other regular lead here, like that. No, you won't use it on doing regular ohms. Just on insulation cord. You're going to switch over to these 2, and you go to ohms, and now touch the leads together. Make sure that it has a low resistance, and it does 0.3 ohms. So that makes the test lead fine. Now put the clips on there and do the same. Come over here and check this one through it. This is the one that this is a good meter. And so now he's going to check resistance through the winding. He's going to check it through them, going through the motor, 1 to 2, 2 to 3, and then 1 to 3, checking the continuity through them. 4 windings in series in each situation. He's finding out, do you have continuity or do you have a broken winding inside the motor? And in this case, you're going to be experiencing a balanced resistance reading in all 3 cases. You got 20.8 ohms. Okay, you go to the other combination, 20.7 ohms. See that? And if you do the other reading, and it's 20.7 ohms. So in each case, you were a little bit over 20 ohms reading. Do you see that there?
Got my finger.
You see that there in the numbers. So in all 3 readings there, you're reading between 20 and 21 ohms in 3 directions. And what that means is you got roughly 5 ohms per winding. You got 4 of them in series. You got about 5 ohms per winding, and that's okay for a motor that size for a small motor. When you go to a bigger motor, the larger the motor it is, when you get above, this is a 3/4 horse. If you go to a 5 or 10 horse, the wires are much bigger and the resistance is much less. So them numbers ain't going to be no 20 ohms. They're just going to be way on down. It might be down around 1 ohm or 2 ohms because the windings are really big and they got very low resistance. So these numbers are going to over here, the 20.3 or whatever it is, you write those numbers in there, and they're supposed to be what you consider to be balanced. They need to be balanced numbers. If the resistance on these is not similar, then there's something wrong with the winding. Okay? Does that make sense? What do you think would be? Would you say it's okay? Listen here. If you come up with this thing here, yeah, the first one's going to be greater than 550 megohms, and then these 3 are going to be just in that range. You put that down in there, what you read through there in ohms. And let me ask you a question. When you check through there on the second test there, what do you think? What would you tell me if you read 21 ohms here and 21 ohms here, but 21 here, and you read like 100 ohms here and 100 ohms here? Something's wrong down in here, isn't it? That means you will go check your wire nuts again. Make sure your wire nuts are good, because you can get condensation in there, build up in these food processing plants and all, and it may be the wire nut itself generating resistance. It can be. So you would take the wire nut off, restrip the wires, clean them up good, put you a fresh wire nut on there, and then try that resistance reading again. It could be something as simple as the darn wire nut connection that could be the issue going on. Seriously, it can be a high resistance joint due to condensation or corrosion. So whatever the resistances are, they should be balanced. Those 3 readings should be very similar to each other. That makes sense? And if they are, then the windings are in the same condition, or I would consider them to be healthy windings. You don't have one of them that's kind of breaking down and the other ones are okay. You don't have a bad imbalance there. So if you have an imbalance in resistance here, here's what can happen. Here's the symptom when the thing runs. It's when you go check the amps, when you go out here and check the amps, and watch this. If you got, say, 20 ohms and you got 100 ohms and 100 ohms, you cut that thing on and you run power and you check the amp draw, the amps is going to be very much unbalanced. So your amp draw coming from that starter, when you check the amps leaving that starter per leg, them amps, they're not going to be balanced, they're going to be unbalanced. Now listen real good here. Let's say, for instance, you got that motor ain't acting right, okay? And you check them, each one of these legs here to ground, check the voltage. And you get the proper voltage to ground, okay? So they're balanced. But yet when you check the amps, they're not balanced. When you go in and you do that resistance check that we just did, and you find out if there's something going on internally in that motor with resistance issue, you can test that from the starter out through the conduit by taking the wires off of the starter and doing the resistance test through the conduit, through the wire, and through the motor, and back up, doing a test that way through the entire run of the conduit. If you see an imbalance of resistance that way, go straight to the motor, unhook the wires, and do the same exact resistance test at the motor. And do the resistance test through the motor. And if you still have an imbalance problem, it's actually in the motor. It's not the conduit. Check it. If it reads good here, resistance-wise, but it doesn't at the original point, way over here for the wire, you got something going on with the wire. You know what I mean? So you got to consider that too, because you got, wire and the conduits is in the picture, the windings in here. The symptom would be, I would look for is if the voltages look good and they are balanced, but yet the currents are not, then you're looking at either wire problems or the windings are going bad. If the voltages are not balanced, if you got a weak leg here, look, you got to go on top and check them. So if they all look good here, and you got a weak leg down here, it's either the overload relay going bad or one of the contacts going bad. Then you can go in between. So if they read good here, 1, 2, 3 reads good, and you get, say, a bad leg down here, go in between them to where the contact joins with the overload, and probe it in here and check 1, 2, 3 between. So if it reads good, 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 bad, good, good, bad, good, good, it's going to be this contact in the contact, right? But if it reads all good, bad, good, good, it's going to be a bad leg in the overload relay. Then you replace just the bottom. That makes sense? Okay, good. So that gives you an idea how to test, do an insulation test. Now, this file here is an electronic insulation multimeter or megameter. We've got one that cranks this a hand wound megameter. I'll get that out next time, and it's the old style that doesn't use that. You crank it, okay? So we'll let you use that one because sometimes you may not have one of them where you work at, but you may have the crank side. Okay? And it generates the voltage without battery. Just sit there and wind it like that right now. We'll do the same thing. Okay? Any questions? Okay, so everybody get your numbers down. Let's see your numbers when you write all that stuff down. Right. Get your name on there. That's going to be a 100. Keep that. And look, the same test can be done on Delta as well. But when you do it, it goes high voltage with the 7 up. You make a test. You put the highest voltage on there from that meter. Go ahead and shoot on the highest range and wire to the highest range. You get that test. You keep these. Remind me to show you a Delta motor back in this cabinet for Tuesday. And then actually see the Delta right on that. And, does any of y'all take the welding classes right now? Okay. You're going to say there's a Delta wound motor. The air compressor, the welding shop behind the old welding shop, that big compressor's got a Delta motor on it. It says right on there. The whole degree. You got to get it. And look, y'all, listen about your worksheets. You know, make sure that you get caught up on worksheets. Time's almost out.
I'm gonna try to do mine tonight in class.
Better get them done, because man, we ain't got next week.
I don't know if Justin's gonna be here tonight or not,
Right.
because something with his daddy.
Yeah,
I think, did he tell you about that?
his daddy was something going on there. Yeah.
I think I did all of it.
Yeah. You're staying up good, but it's, I'm concerned. Everybody's not. Some people wait for the very last minute to do any of it. I don't know how. I mean, I can't live like that, you know.
All right, let's do
Good deal.
this. Good
Thank you.
information.
Yes, sir. So you picked up anything new?
Oh, yeah. We don't use the make at work. So most people don't know how to use it.
Right.
So that helps. This helps. And if you don't use it, well, I'm not gonna learn this now. Next year, if I don't use it for a year, then
You can forget. Why don't you take an extra one of these, and you can clean copies of them. Go to the plant, make some photocopies, and you can teach them guys how to do this. You take clean copies there, and maybe you can take some snapshots on your phone, and you can share them. You can then text them to people. And we're going to get into the Delta. I'm sure you've got both of them in the plan.
I've only seen the wires. Unless we got filters on the compressor.
The Deltas have a higher starting torque, and they're using on things have to have a super high starting
I
torque.
think we do have filters on the compressor. They're like,
I know that Schindler, what they have, they make escalators. A lot of people escalators. Everything they got there. So, anyway, thank you. I'm glad you picked up something that's smooth. That's what I like. When you get something new, I want to be worth you. You got to ride it up.
I got the number of this meter too.
This is a very good meter. It'll also do frequency. If you go to hertz, if you go to AC volts, and hit hertz, it reads the frequency of whatever. If you're checking a drive, a VFD, it'll actually tell you hertz. Check capacity, get in the blue function. If you go to ohms and hit the blue button, it goes over to farads. It'll check capacitor. Like on the back of the motor here, these. You pull that off and you got a discharge. You set that capacitor there in with the second function. It'll do temperature in the second function in Fahrenheit with a probe. You got to plug a probe into it. It'll be temperature. If the minimum maximum, if you're doing voltage and you want to get a minimum maximum reading, you hit that, and over time it'll store the lowest readings. Where's it at? It'll toggle from minimum to maximum. Min, max, average, max, min, average. So if you want to check amps on something over a long period, you put your amp plug in, you put it in that mode, that's going to store the average and then the max and then the min. It'll store all that over a long period of time. So it's a very nice meter. I would buy one for sure. It is very good. They're about $750 to get it. Get the case with it, get all your stuff. It's probably around $900,000. It's worth it. So, okay, yes sir. Thank you. We'll see you Tuesday. Yeah.
You done recording?
Not you. I get cut off right now.
I ain't want to get me on it.
Okay.
Tension. Test my tension on my belt.
You need it.
Where they?
Got it right here.
I never used it. I want to see how.
Ask John if he remember how to use that. If he does it, I'll show y'all. Hello? Okay, sorry I had the camera upside down. Okay, so we're going to close out now, and this is Durwood King with Sampson Community College. This is the MNT 110 class, maintenance procedures. And if you have questions about what we just went over doing the motor testing, let me know. You can contact me at dking@sampsoncc.edu, and those of you that are students have my cell number. You can call me. And if you happen to be watching and you are not connected with the school, you can contact me. We can try to get you into either our degree program or some certificates that we have. And I'll be glad to help you. We have electrical certificates, and we have a full degree in industrial maintenance that covers electrical, mechanical, welding, refrigeration. It covers a little bit of everything in a 2-year degree. We've got an electrical degree, 2-year degree in electrical systems. We got a degree in HVAC, a welding degree, a lot of stuff, kind of whatever you're interested in, whatever you feel kind of draw toward, then we can probably get you in a good program that you would enjoy and have a rewarding career. So thanks for watching, and again, have a blessed weekend. Thanks for watching. God bless you.